And hello. Welcome to my one class session. Again, my name is Joey. I'm going to be your chemistry teacher for this section. Today we're working on chemistry 11. We stream chemistry, grade 11, grade 12 chemistry once a week on Wednesdays at 10 a.m. and back at noon in the Eastern time. So feel free to join us for this session. Again, here at one class, what we're doing is we're dedicated to online learning. And what that means amidst all the school closures now is that we're preparing students to either get ahead or to catch up in terms of material if at their own pace. So they can come back, they can watch the video either live or on their own time. And hopefully here at One Class, what we're doing is we're providing some educational resources for those who have access to the internet and for those who are motivated and want to kind of get ahead in school. Again, my name is Joey. Just a little bit about me before we start. Again, I'm a teacher candidate at York University. I'm just about to graduate now, and I'm going to graduate in the secondary school education division. So I'm qualified in intermediate senior, and my teachables are chemistry, so science, and in music as well. And I'm hoping to hopefully get my math teachable further down the road. So without further ado, let's get started on our lesson today in grade 11 chemistry. So what we have today is, if you remember from last week, for those of you who tuned in last week to my lesson as well, what we talked about was we did a little review. We talked about the course outline, and we talked about matter trends, and this is kind of the first unit that we're talking about. So again, we reviewed what the periodic table states. Again, we reviewed what an element is, metals, nonmetals, metalloids. So we're familiar with all of this stuff, and a lot of this stuff is review, right? So if I look at the periodic table here, again, we know that the first column here, or the first group, is the alkaline metals. We know that the second group, in this case, is the alkaline earth metals. The halogens in group 17 and the noble gases in group 18, right? So we're all familiar with that kind of with this arrangement of the periodic tables, and we know it's by atomic number, so by the number of protons, and usually by atomic mass as well, and that's what Mendeleev kind of did. So we're familiar with the modern periodic table here, with all of these groups. We're also familiar with the properties of these elements as well, with the alkali metals being very, very reactive with water, and they also react with the halogens. And we'll talk about ionic and covalent compounds probably maybe next week or the week after, but in terms of properties of those, we're familiar with that. We know alkaline earth metals from oxides, or they react with acids. They're also metals that have metallic properties such as ductility or malleability or luster. We know halogens and noble gases. These ones have 7 valence electrons, right? For halogens, right? You know, it's group 17, so it has 7 valence electrons. Alkaline metals have 1. Alkaline earth metals have 2. Halogens have 7, and noble gases have 8 with the full octet, right? So that's what we learned in either a previous class or our last week. So again, they could be either stable, usually gas in room temperature, and they react with hydrogen or with metals as well. Noble gases are extremely unreactive. So we have kind of these 4 groups. There are transition metals as well, when they tend to have a multivalent. Some of you might have learned that in your previous science course, where, for example, copper has a charge of 1 plus or 2 plus, depending on its oxidation state. And we'll talk about transition metals more so when we talk about naming and how we find chemical compounds and how we name them. So that was review, and we reviewed this model of the atom. We talked about we reviewed what a Bohr-Rutherford atom or diagram was. You probably did that in your previous science course. So we did Bohr-Rutherford diagrams, and then I actually introduced you to this topic of isotopic abundance, and we're going to do actually a couple of questions. I have a question here, and I'll have 3 questions for you to do in terms of isotopic abundance, because this topic is very, very, very popular in unit 1 when we talk about for the assessment at the end of the unit if you're doing school. So again, this topic of isotopic abundance, we'll do practice problems of those ones, and then we ended off the lesson next week with modern atomic theory. So we talked about how we have a number of subshells. So it's kind of like the Bohr-Rutherford diagrams, but instead of we talked about these shells being energy states. And we talked about how we have ground state electrons where they have the lowest energy level, and we have valence electrons which have the highest energy level. And valence electrons are responsible for chemical reactions, for bonding and whatnot, mostly for bonding, but I'm gonna introduce you to the concept of how ground state electrons can sometimes jump into a higher energy level, and how higher energy level electrons or valence electrons jump back to the ground state, because usually that's the case, right? Valence electrons are high energy; they want to go to a spot of lower energy, right? So they emit some type of energy once they transition into a different energy level. And we'll talk about more of this in grade 12 when we talk about structures and properties, and how modern atomic theory kind of explains itself. But we'll get back to this. But just for now, just know that this is kind of how we visualize an atom now. Or we know Bohr Rutherford was the different shells, and the valence electrons go into the different orbitals, or the different shells. But now what we have is we have shells, and we have shells, and this is actually it coincides to the energy state, or the energy level of that electron, and that's all you need to know for kind of modern atomic theory. We kind of go into deeper in grade 12 as well when we talk about wave particle duality, when we talk about Schrodinger's equation. And his kind of model of the atom. So let's talk about this first. I have a couple of practice problems here. Let's talk about the isotopic abundance, and we'll do practice problems with this one, and then we're gonna move on to trends in the periodic table. So let's do a couple problems here with with isotopes. So remember, isotopes here are atoms of an element that differ from each other only the number of neutrons in their nuclei. So for example, we have carbon 12 here, which is the average or natural abundance of carbon. As you can see here, carbon C is 6 here, right? We know if you look at the mass, it's 12.011. That's the natural abundance, or the average atomic mass, right? So if we have that, and what if we have carbon 14? So carbon 14, it's still carbon. It still has 6 protons and 6 electrons. However, its mass is different. It's 14, right? Its mass is 14, so it has the mass of nitrogen in this case. So it's a different mass, and the only time the mass changes would be either an increase of protons or increase of neutrons. If we increase the protons, it would be a different element. So if we increase the neutrons, then it is indeed an isotope. So that's just a review of what an isotope was from last week. And then we're talking about this topic of isotopic abundance. So what is that? So again, we have the isotopic abundance, or natural abundance, refers to the percentage of natural occurring isotopes of an element. So the listed atomic mass of an element is its weighted average. So every time we look at an atomic mass, let's say aluminum, for example. Aluminum has a mass of 26.982 Al, right? Number 13 here, 26.982. Aluminum doesn't actually have a mass of 26.982. It is just simply the weighted atomic mass. Weighted atomic mass, or the average of its isotopes, gives us this number. You can't just say, I'm going to take one atom of aluminum, and I know for the fact that that's 26.982. That's not how the concept works. It works in terms of a weighted average of all the isotopes. So for example, we could have aluminum maybe 28 or 29, or aluminum 25. If we average all of those isotopes together, and their isotopic abundance, so the percentage of which they occur, we average that out to 26.982. So that's kind of how we do it. So based off that, there's a lot of questions when we talk about percent abundance or isotopic abundance. So let's look at this first one here. So we have Cu63. So Cu, if you don't know yet, Cu is copper, and copper exists in copper exists at number 29, right? So it's 63.546, or atomic number 29. Here's copper, right? So here, copper, Cu63. And what does 63 mean? Here, 63 means the mass, or the atomic mass, right, of that. In this case, it could be an isotope, right? In this case, it's not, because it's actually 63.546. So it's just what the atomic mass is. So it's 63, and then they clarify what the atomic mass is. So it's 62.9296, and then they round up to 63. So copper 63 and copper 65, which has a different mass. So you're given these two masses. so copper is made up of two isotopes. It's made up of copper 63 and copper 65. So if we're given that the copper's atomic weight is 63.546, what is the percentage abundance of each isotope? So how do we solve this problem? So what we have to do is we are going to solve this through, I'm gonna give you a formula, and this is how we're gonna solve it. So my formula here, I'm gonna write this out. Hopefully it fits, but this is we're talking about. So we're gonna do average. So this is average atomic weight equals. I hope this fits. So that's going to equal. We have the mass of the isotope. So I'm going to say here, this is isotopic mass times the percentage abundance. So multiplied by, I'm going to use the percent sign for percent and then percent abundance. So I'm going to multiply it by, and I'm going to multiply by percent abundance plus, and then again, it could be another isotopic mass. So it could be plus another isotopic mass times the percentage, and then plus, if there was a third isotope, I would add another one, right? So you have average atomic weight equals isotopic mass multiplied by the percentage abundance plus the isotopic mass times abundance, right? Basically what it is average atomic weight is we have all of these, the sum of all atomic mass multiplied by the abundance. That's what we have here. So let's solve this, right? So let's solve this. So what we have here is the average atomic mass what is given here, right? And I'm going to do this in blue. It's given here, right? It's 63.546. That's the average atomic weight. So we have 63.546 equals, and what do we have as our isotopes? We have our isotopic mass in this case of Cu63 is 62.96. So let's do that. So this is 62.9296. And we're trying to solve for each of the percent abundance, right? So we're going to leave this as, let's just leave this as X. So I'm going to denote this in black, and I'm going to call percentage abundance X. This is X. So I'm saying let X be percentage abundance plus, and what do we have here? Isotopic mass of the other one of copper 65 is this mass here, right? So we have 64.9278, and then times the percentage, right? So would I actually would this percentage be equal to this percentage? No, it wouldn't be, right? Why is that? If I had the same percentage if I chose one variable to be the percentage for both the percent abundance for for copper 63 and for 65, we wouldn't get the correct answer. So how do we denote this variable here? What will we write here? And how will we show that algebraically? So I'll just do a little aside here, and I'll do a little aside. Maybe up here actually. So remember, isotopic abundance is the percent of abundance, right? So what we can say here, we can say 100%, because it has to add, everything has to add 100%, right? So it equals, you can say it's, or actually, sorry, you have to say, in this case, it's X plus, and then you can say maybe Y or something equals 100%, or you can say equals 1, right? Because it has to be, I'm convert everything in decimals, right? And I'm going to say, oh, let X be the percent abundance for copper 63. So X here would be the percent, so let X equal percent abundance for copper 63. And then I'm actually no, I won't use Y in this case. Actually, sure, I'll use Y. Why not? And then what we're gonna do is I'm gonna do let Y equals the other one, right? So I'm gonna write here. I don't have a lot of space, so let Y equals percentage abundance for this would be Cu65. So basically, I have two variables here, right? So I'm going to write here, which means percentage abundance of copper 65 here would be Y, right? So I can say this is a Y But now when we have two variables, right? You have x and y. How do we solve this? Right? You might say, well, how do we solve this? Is we're going to rearrange this top equation here with x plus y equals 1, right? So what we can do is we can let's bring y to the, or let's bring x to the other side. So we bring x to this side. We have 1, or we have y just by itself equals 1 minus x, right? And what we can do is we can substitute this this other equation for this y here, right? And that's what we're doing. I'm not going to put the arrow, but we can substitute that into that equation, into this y here, right? So that's what we're doing. So let's do that. So we have 63.546 equals, and we have, I'm gonna do this in red. 62.9296, and then we're leaving this as x, right? We just want to have one variable so we can solve. So this is x plus, and then we'll do this in red again. This is 6 was really bad. 64.9278, and then now I can set it in terms of x, right? So I can say here, if y equals 1 minus x, then I can simply do 1 minus x here and leave it like that, right? So now we have a system of equations. Now we have or not system of equations, but we have one variable. So now we can solve, right? So how do we solve this? And I'm going to do this in, I'll do this in the same color. But we can solve this through, we can expand this, and then we can collect like terms, right? So it's simply what we've been doing in kind of grade 9 math, right? So this is equals 63.56 equals. It's a lot harder when I have to switch colors actually, but hopefully some of you in the chat will find this nice. So 62.96 x plus, and then I'm going to expand all this. So I'm going to just use the color black now. So if I have, I'm using distributive property, right? I have 64, I'm going to multiply it by the 1 here, and then multiply it by the x here, right? So it's 64.9278 minus 64.9278 and the x, right? So that's what we have for our expanded form of this question. And now what we could do is we collect like terms, right? What I can do is I can collect these two, this term, sorry, you can't see this x term and this x term together, and I can bring this one to the other side. So I have numbers on the other side. So let's bring all the numbers to this side, to the left side first. So I'm going to bring this number to this side. So I'm going to subtract both sides by 64.928. I'm going to take out my calculator. 63.446 subtract 64.9278. I'm left with, this is -1. On this side, I'm going to just use all black now. -1.3818. Sorry, the 8 was really bad. 3818, and that's going to equal, and I'm subtracting these x values, right? So this here minus this here, right? So I have 62, and it's just simply just algebra, right? 62.9296 minus 64.9278. That's going to give me -1.9982. Negative 1.9982, and I still have the x here, right? And we're trying to solve for x. So if I divide both sides by -1.9982, what am I left with? I'm left with, so what will x equal? So I'm taking -1.3818, and I'm dividing it by -1.9982. I should get a positive number in this case, and I do. I get, this is 69.15, right? That's kind of my answer in this case. So this is, so this here is 69.15. Maybe I'll round to, let's say 2 decimal places. Actually, maybe I'll do 4. No, let's do 2 decimal places. So my answer here I'll show you actually, because I'm skipping a step here. This is 0.6915. It's going to be around to 4 decimal places, and which will equal, actually no, I have to do 5 decimal places, and the reason why is a significant digit. So that's actually what we did last week, right? I totally forgot about that. So if we look at our question here, we're given our AMU in terms of our AMU. I have 1, 2, 3, 4, 5, 6 significant digits in this case. I have here 63.546. This is also this is 5 significant digits. So I'm actually going to use 5 significant digits in this case for my answer. So this is 69. So 0.69152 is what I got in my calculator. And what I can do is I can change this to percent, right? So I can move the decimal 2 places. So I get 69.152%. And that's my percentage for, and what was X here? I said let X be percentage abundance for copper 63, right? So am I done yet? I'm not done. I only have one percentage, right? I only have percentage of 63 points, copper 63. I need percentage of each isotope. So you have to read the question carefully, right? So again, here, this is my, this is copper 63. So I'll do this in blue. This would be my percentage abundance for, this is copper 63. So how would I solve for copper 65? How would I solve for this one? Well, I have, I know that y equals here. I'm trying to solve for y now, right? I remember that's why we did all this business here. Y equals 1 minus x. If we know x here, we can solve for y. And y was copper 65, right? So if I do that real quick, remember here I denoted y as my percentage abundance for copper 65 equals 1 minus x here. So that equals 1 minus, I have x here. This is 0. I'm going to keep this in decimals. So 0.699152. And then I'm left with, let's check. So this is 1 on my calculator, 1 minus 0.69152. And I'm left with, this should be about 0.30. So 0.30848, which would equal, if I move the decimal 2 places to the right, I get 30.848%. And this would be for copper 65. So that's kind of my answer for, that's how you approach isotopic abundance questions in this case. So this was kind of this is a long-winded question, or not really long, but this is how you go about solving these types of questions in this case. Let's do one more. I had 3 questions, but I think for the sake of time, let's just do one more because I do want to get back to trends. I want to get to trends today. So it says here a sample of naturally occurring silicon. So we're talking about silicon now. So silicon is a metalloid and belongs in this side, right? It's topic number is 14. Of silicon consists of silicon 28, and we get the mass here, silicon 29 and silicon 30. If the atomic mass of silicon is 28.0855 and the natural abundance of silicon 29 is 4.67, what are the natural abundances of silicon 28 and 30? So that was a lot of words. So let's write this in terms of a mathematical equation. And I'm just gonna go back to our formula real quick. And this is our formula, right? We have average atomic mass or weight equals isotopic mass, the sum basically of isotopic masses times abundances. So I'm gonna rewrite that for all of you here. So average atomic mass. So I'm gonna do AAM as average atomic mass just to save space. And I hope you can follow along here. In this case, this is AAM. So average atomic mass equals. So this is isotopic mass. Isotopic. So in this case, I'm just going to write SI28 in this case. So SI28 times the percent abundance plus, this would be SI29 times the percent plus SI30 times the percent abundance, right? But percent just means percent abundance. I just don't have enough space on my half a monitor to write out percent abundance, right? So if I substitute some of these numbers in, so if my average mass is 28, it's 28.0855, right? So 28.0855, that equals silicon 28 here is 27.9769 times the percent. That's what we're trying to solve. Plus silicon 29 here is 28.9765. In this case, we do have the silicon natural abundance. It says here 4.67. So let's change that into decimals. So 4.67. If I divide by that by 100, I get 0.0467 plus, and then silicon 30, right? So Si30, which is this mass here, right? I'm running another space here. That's 29.9738 times the percentage, right? So I'm glad I fit all of that in. But I need to figure out what are these percentage. I need to write them in terms of a variable, right? But before we do that, I'm going to do this in blue. Let's determine an algebraic expression that could help us determine how to denote these variables. How do we denote these variables? How would we? So remember, all of the percentage abundances have to add to 100, right? And I'm going to do this in blue. So it's going to be 100 or 1 equals percent abundance of this, of silicon 28. So let's denote this as X. So we can say let X equal percent. This is a Si 28% abundance. I hope you, it's not 28%, it's just silicon 28%. Percent abundance. I hope you can follow along there. I know my notation isn't the best here, but I just don't have enough space, unfortunately. Or maybe I'll do percent. Maybe this might be confusing. Percent Si28. That might be a bit better. So I see that, and then I'm gonna let Y equals because we already have this percent abundance for 29. I'm gonna let Y equal another variable equal the percent abundance for silicon 30. So this is percent for silicon 30. Right. Now what we can do is we can create an algebraic expression. So remember, they all have to add to 100%. So this is 1 equals, so this is X plus Y plus, and then my last abundance here is, this is 0.0467, right? Because remember, this also plays a part in this whole, remember, all three of these isotopes add to 100%. So how would we, let's isolate for one variable. So we want to rewrite these in terms of one variable. And last time what we did was we wrote Y in terms of X, right? We had Y here and we wrote it in terms of X, right? So actually what we can do is we can erase this and we can put variables here. So I'm going to put, I said let X equals this percentage. So this would be X. And then this here would be Y, right? So now what we have to do is we have to arrange Y in terms of X. So how would we do that? We would have to move X and the 0.0467 business to the left side, right? So we're moving this to the left side and this to the left side as well. So we have 1 minus X minus 0.0467 equals Y, right? And that's what we're going to solve. That's what we're going to plug into here. And for this Y here. So that's what we have in this case. And then what we can do is and now we have one variable, and then this is all just algebra, right? So I'm going to rewrite this entire equation. I'll rewrite this here. So this is 28.0855 equals, this is 27.9769x. Maybe I'll keep the variables in blue for you. Times x, and then plus, and I can actually do this calculation for you because it's just two numbers, right? So I can do that on my calculator. So this is 28.9765 multiplied by 0.0467. This will give me 1. This is positive 1.3532 0. I'm going to choose to keep 5 decimal places because we have how many significant digits in this case. I don't want to make a rounding error. We have 6. I see 6 here, 6 decimals. So we have 1, 2, 3, 4, 5, 6. Okay, good. And then we have this last part is just simply 29.9738, and then that's going to be, and then it's being multiplied by y, which is 1 minus x minus 0.0467 here, right? So again, I'm running out of space, but that's kind of what it is here. So what can I do? I can expand this one. I can expand this first, and I can move this this guy to the left, right? So I'm going to do both those at once. So I'm going to move this term here I'm going to subtract both sides by negative 1.38, and then we use distributive property to expand this. So I'm going to do let's do the subtraction first. So this is 28.0855 minus 1.35320. I'm subtracting both sides by that number, and I get this is 26.7323, and that's going to equal 27.9769 x. This is x, and then I'm going to expand all of this. I'm going to put this in black. So this is now 29.9738 times 1, which is 29.9738, minus I have 29.9738, and then the x here, right? And then the x here. And then this is going to be 29.9738 times negative 0.0467. So this would be minus. Then plug in my plug that in my calculator. 29.97 times this is negative 0.0467. I'm gonna get negative 1.33997. I'm gonna round it to 8 here. So that's what we have this really big thing. And then what we have to do is, again, this is all just algebra, right? This is the easier part because we've already set up the equation, right? So again, let's move the numbers to the left side. So let's move this number to the left side, this number to the left side, and then let's collect these like terms, here and here. Let's all do this in one step. So I'm going to subtract. I'm subtracting both sides by 29.97 first. So this is 23.7323 minus 29.9738. So I get some number, and what I have to do is I have to add both sides by 1.39978, right? So I'm going to take this answer and add 1.39978. So you should get something like negative 1.84. So negative 1.84172. So so all my numbers are on the left side now, and then I just have these two variables, right? I have 27.9769 minus 29.9738, and I'm gonna get negative 1.9969 x. Oh, sorry, what happened here? 1.9969x. And then what I could do is I could divide both sides by negative 1.9969, right? And then I'm going to get x by itself. So x would equal 0.9222. I need how many decimal places? I think it was 6, right? 92290. Is it 6 decimal places? And it's 4.67, so this is actually 3. So I have 0.922. And if I convert that into percent, my x would equal, this is 92.2%. And we said let x be the abundance for silicon 28. So this is my percentage abundance for silicon 28. And now all we have to do, because we have the isotopic abundance for our silicon 29, we have to figure out what silicon 30 was, right? And what we can do is we can actually reuse this equation here. We can reuse this equation here to solve for that, right? So let's do that. Because we're given our x now, so we just have to solve for our y. So I'm going to rewrite this. So I'm going to do this at the bottom. This is y equals 1 minus x minus 0.0467. And then we have y equals 1 minus, we know x is 0.922. Minus 0.0467. I'm choosing here, I'm not taking that many decimal places. So in this case, I could, because this is not the final answer. So what I could do is I could take some decimal places for this x value, because it's not 0.922, it's technically 222 and then 90. So I'm taking more decimal places to avoid a rounding error in this case. Oh shoot. Sorry about that. 0.0467. So y would equal, and then I can just shove this in my calculator. 1 minus answer minus 0.0467. So my answer in this case would be 0.03. I'm taking 3 decimal places, or you could say this is 3.1%. And this would be for our silicon 30, right? So this is silicon 28, this is silicon 30. Why was silicon 30? So what we have here is we have our isotopic abundance for silicon 30 here. Or actually, I'm gonna circle it. We have it here. We have our silicon abundance for 28, and obviously in the question they already give us the silicon abundance for silicon 29, which is, if I were to change this into a decimal, this is 4.67%. And what we could do is we could actually check. We could check all if it adds up to 100, right? So we have silicon 28, which is 92.2, plus 29 is 4.67, plus 3.1 here for 30, and it should equal 100%, or very, very close to that. If it doesn't, we might have rounded up or rounded down, but ideally it should make up 100%. You might get a little bit of a rounding error, but it's very, very close enough. So that's kind of the topic of isotopic abundance. I hope these 2 questions really helped you in terms of how do we write the variable. I find that a lot of students struggle with that part first, where we know how to set up the equation, we know how to do this part, the first part, but once we get to the second part, it's a bit harder, right? We don't know how to set up these equations in terms of x, in terms of y, or in terms of specific isotopic abundance. So the trick here is to just relate everything to 100%. We know it's a percentage abundance is like a pizza, right? So maybe half of it is a Hawaiian, a quarter of it is barbecue, and a quarter of it is pepperoni. We need to be able to find out which part of it is pepperoni, which part of it is pineapple. So we can say, for example, y is our pepperoni pizza, and x here is Hawaiian. So how do we figure out pepperoni pizza? Well, it's simply just 1 minus our Hawaiian, or the whole pizza minus the Hawaiian pizza minus my barbecue pizza would equal my pepperoni pizza, right? So something like that is how I would visualize algebra, and that's how I usually visualize algebra in this case, in terms of percent, right? It all has to equal 1. So that's kind of isotopic abundance, and that's kind of that's very much these questions here. So what we're going to do is we are going to move on to trends and the periodic table. So I'm going to start with some notes here. So I'm going to briefly talk to you about these trends, and then that's probably going to be the lesson for today, just because we're going to run out of time. We did take about like half an hour to 40 minutes on these 2 questions, but I'm really hoping that for these 2 questions, they'll help you determine these isotopic abundances with confidence, and because it's a very, very good test question that a lot of teachers usually put. So let's just go over this for a sec. So this is trends in the periodic table. So our first trend here, and the most important trend in this case, in the entire trends, is atomic radius. You can always refer everything back to atomic radius. So I'm gonna write this down. So this is atomic radius, and a lot of trends here is actually, it's about logic, and it's about how each property affects another property, and so forth and so on. So atomic radius here is basically how, in layman's terms, if we talk about the scientific term, obviously the distance between the nuclei of bonded or adjacent atoms of the same element divided by 2 represents atomic radius. That's the formal definition. How I usually put it is how big the atom is, right? This is how big atom is. That's the very layman terms, right? Obviously the radius the radius matters, right? Because if you put kind of two atoms, like two hydrogen atoms in this case, I have the radius of one of the hydrogen atom and the radius of the other one, right? So again, you have what it says here is the distance between two nuclei of bonded or adjacent atoms divided by 2, right? So you have, sorry, that's not big enough, but in reality, when we're measuring how big an atom is, it's H bonded with H here, the nuclei of this one and the nuclei of this one. So this distance here, and it's going to divide by 2. So half of this distance here would be the formal definition of an atomic radius. But layman terms, how big an atom is. That's the technical definition, but how big an atom is. Right. So again, if we look at our periodic table, and this figure 6 is pretty good because it gives us what the trend is in this periodic table. Actually, so hold up. Let me put here. This is my title. This is trends in the periodic table. Trends in periodic table. So again, we have atomic radius, so how big an atom is, right? So the trend here, and it says here, right, down a group, atomic radius gets larger. So I'm going to write here, so down a group, it would increase, right? So I'm going to write arrow would increase. And then across a period, so across a row, or across a period, it would decrease. So what does that mean? What does that mean? So let's take two elements, for example. Let's look at this column 1 here. So for the first one, how do we prove that this increases? Let's take a look at lithium and sodium. So Li 3 and 11 here, lithium and sodium, because we're talking about down a group, right? So let's take the group 1 elements. Let's take, this is lithium versus sodium. So how do we know it's bigger or smaller? So let's draw, we're comfortable with drawing Bohr-Rutherford's diagram. So let's draw Bohr-Rutherford for lithium. So I'm not going to write we don't care about the protons in this case, but so we have lithium here. Our first shell has 1 and 2, and our next shell has a valence electron 1. That's a really bad circle. Sorry. So it has 2 shells, right? It has the first shell, the first energy level has 2 electrons, the second energy level has 1. What about sodium? So sodium here, I have the first shell going to have 1, 2. The next shell, I have 8, right? And how do I have 8? I have to go across, I have to account for all these electrons before I hit sodium here. So I have 8 in the next shell. So 1, 2, 3, 4, 5, 6, 7, 8. And then my next shell, this is a really bad circle, has 1, right? So as you can see here, based on the number of shells, it's bigger. Sodium is bigger, right? So I have 1 more shell that comes in. And look at my drawing is very, very weird, but if you look at it, it's much bigger than lithium, right? So it means if I have potassium, I would have another shell, and then rubidium and cesium and francium would keep adding shells with one extra valence electron, right? So in this case, it increases, atomic radius increases as I go down a group, down a group, right? So that's how I prove to you that this trend exists. So again, here, down a group, it increases, right? I'm gonna write here, my example here was lithium versus sodium, right? So that was my example. And if you check it with halogens, alkaline earth metals, or noble gases, you're going to realize it's the same thing. I'm going to get a different shell or a new shell every time I go down a group. So that's good. So what about across a period? How do I prove to you that this, why does it decrease? So let's take a fluorine and neon. This is the same row, right? We're doing the same period here, across a period. So let's do fluorine and neon. So let's do fluorine and neon. Did I do that in blue? No, I did it in black. So let me do this in blue. So why does it decrease across a period. So this is fluorine versus, I said it was neon, right? Let me double check. Yeah, this is neon. So let me draw the Bohr-Rutherford diagrams for you just to see what those two look like. So for fluorine, I'm going to do this in blue. Sorry, I told you blue. So for fluorine, we have first shell is 1 and 2. Second shell is 7, I believe, right? We have 1, 2, 3, 4, 5, 6, 7. We have seven valence electrons in fluorine. So 1, 2, 3, 4, 5, 6, and 7. And then for neon, obviously because it's the other element right beside fluorine, I'm just going to add. I'm going to get one more valence electron to make a full shell because I know neon's a noble gas. I'm sorry that my circles are really bad here, but I blame the tablet. I'm sorry. 1, 2, 3, 4. This is 8, right? 8 at the end. So you might say, oh, is it neon supposed to be bigger? Like I'm looking at it visually, it kind of looks bigger. I have more electrons, right? Shouldn't it be bigger? Like atomic radius increases? No. And why I say that is because of this point. More protons added to nucleus increases effective nuclear charge. So what does that mean? So it means that if you think about these nuclei, so I'm gonna erase this N and erase this F here, and we know that this is and I'm gonna do this in red. So we know that actually hold up, let me relabel these. So remember this is F here and this is neon, right? This is fluorine and neon, right? And then I'm going to do this in red. So remember, this here is a positively charged nucleus, right? And in this case, I have in fluorine, I have what, 9 protons. So I have nine protons, right? And in neon, I have 10 protons, right? Sorry, I wrote no for some reason. This is 10 protons, right? So again, in this case, neon has a more positively charged center. So what it does is it likes to pull electrons towards each other, right? And this is based off the attraction rules, right? Remember something that's positive attracts negative, right? Or what we can say here is opposites attract, right? And that's kind of what magnetism in charges. Opposites attract, and then like charges repel, right? And these are all charges repel, right? Or repulsive. So if opposites attract, there is a charge here between, I'm gonna use black, between this positively charged and these electrons, right? So there's a force that is there's a force of attraction with the center of the nucleus and these outside electrons. So if I have a more positively charged center, it's going to pull electrons towards it. So what it does is it increases effective nuclear charge. So in this case, if it pulls towards my nucleus, my shell will get slightly smaller, but not less smaller, right? And we know that through here. We have fluorine here, and the neon is just slightly smaller, right? 72 and 71, just slightly smaller because of this effective nuclear charge, because of this attraction between the nucleus and the electrons outside it, right? So again, the positively charged core of the nucleus is the center, and it's going to attract the electrons on the outside. So as we increase the amount of electrons and as we increase the amount of protons across a period, we increase that attractive force. So it pulls it together, so it makes it smaller. So these forces, I'm right here, attractive, or I'm right here, effective nuclear charge. So effective nuclear charge decreases atomic radius. So that's what I have here. Effective nuclear charge decreases atomic radius in this case. It's because it pulls it together. It's more attractive. So, and again, it's still the same shell, right? I still have 2 shells here and 2 shells here. So it's the same in terms of shell. So that in terms of size, not unlike this example, this has 2 shells and this has 3 shells, right? So way difference, right? So look at lithium and sodium, big difference in atomic radius. In this case, very little, right? This attraction force provides it doesn't really affect the trend, or not the trend, but the atomic radii, but does by very little. So we say it decreases as we go down the periodic, or across a period, sorry. As we go across a row, it decreases. So this was my example here. So that was atomic radius. And again, everything comes back to atomic radius. So I'm going to spend more time actually at this point. I don't think we'll get to all the trends for today, but atomic radius is the most important thing, because I'm always going to go back towards atomic radius. I'm going to go over ionic radius really quickly, and that's probably what we're going to have enough time for today. And then we'll go over ionization energy and electron affinity and electronegativity probably next week, and then we'll finish off trends. But atomic radius is really important, so I wanted to spend more time on that. This is atomic radius. So this is ionic radius, right? So what's ionic radius? It's simply the size of the ion. Size of ion, right? And what it is, it's very much the same thing as atomic radius, but it instead of the atom itself, we're measuring the ion size. So as you can see here, it's a measurement of the size of the ion. Again, positive ions are smaller than atoms, right? Positive charge and nucleus pulls electrons tighter. So if, for example, if we had, let's have, so we have, in this case, I'm going to take this first example. So I'd say, so in this case, positive ions, or I'll say cations, and you're familiar with that, are smaller than atoms. So I'm going to show you 2 examples of that. In this case, I'll show you Na and I'll show you Li. Yeah, Li, lithium versus lithium plus, right? And lithium plus is the cation, right? Because it got rid of the one valence electron. So let me do this in. I'll do this after I write out the other one. So it says here, negative anions or anions are larger than atoms. Are larger than atoms, and I'm gonna use fluorine, for example. I don't know why I picked the same ones, but I'll use fluorine. This is F versus this is F minus, right? So these are anions. So I'm going to show you why, and then we're going to call it a day. So why does this first one exist? So let me compare first. This is lithium versus lithium, the cation for lithium. So let's draw again, Bohr-Rutherford diagram. And it changes, right? So for lithium, we know that this is 1, 2, and then 1 on the outside. So we're good for that one, right? So we have 3 electrons, right? We have 1, 2 in the first shell, and then the third one in the second shell. So about lithium plus. So in lithium plus, this ion, we have 2. We're going to lose an electron, right? It has a positive charge, so we lost an electron. We can't change the number of protons, so we just have 2 electrons in this case. And as you can see, much smaller. In this case, it's 1 shell smaller, right? This one has 2 shells. This one has 1 shell. So again, atomic size. This is the ionic radius. Lithium is much bigger than lithium. The cation lithium, or I can say the cations are smaller than the lithium atom, right? And this actually works for, and this as you increase the size, obviously, like a rubidium, sodium, potassium, rubidium, all of these guys here follow the same trend. So that's good for the cation, and I'm going to show you, this is F, and so I'll leave this here, and I'm going to show you fluorine and fluorine minus. So what's the difference between those two? And why does it follow this trend? Minus. So again, my Bohr-Rutherford diagram for fluorine. 2 in the first shell, and then I have 7, right? 7 in the second shell, 7. And then what about F minus? F minus, I have 1 extra electron, right? So I'm going to have 1, 2, and then instead of 7, I'm going to have 8. Oh, that was actually not a bad circle. I'm proud of myself. 4, 5, 6, 7, 8, right? So why is it bigger? Actually, so it looks bigger, right? But again, it's deceptive. It's smaller, right? Remember what I said about effective nuclear charge? These two have the same shells, so I'm gonna write here. These two still have the same shells, right? So this has 2 shells. This has 2 shells. So we can't use the number of shells to determine our size or the radius in this case. But remember what I said before was we have, again, erase this. Remember, this here is a positively charged fluoride, positively charged fluorine. Again, greater number of electrons, more negative charge. Nucleus cannot hold as tightly, right? So in this case, what we have here is fluorine minus versus this is just fluorine, right? So we have here fluorine minus here is bigger. Remember, here is anions are larger than anions are larger than atoms, right? So in this case, this fluorine here is larger than this. And why is it larger? It's not in the sense that it has this effect. It still has effective nuclear charge, but look at there's an imbalance of charges, right? Remember, in this case, we have this effective nuclear charge plays a part when there's the same amount of protons and electrons. We have 10 protons and 10 electrons, you're going to cancel out, right? So the protons are going to pull the electrons closer, so it makes it smaller. However, in this case, how many protons do we have in fluorine? Let's look at our periodic table. We have 9 protons, right? We have 9 protons, but we have 10 electrons in this, in F minus, in this anion, right? We have 1, 2, and then 8 on the outside. 2 plus 8 is 10, right? So because we have 9 protons and 10 electrons, there's greater number of electrons, so there's more negative charge. So their attraction between the negative and the positive is less, right? So the electrons are going to push further apart because it has a more negative charge, right? It's not repulsive, it's still attractive charge, but because there's no balance, not 9 and 9 or 10 and 10, the electrons have a greater number of electrons. So it actually extends, that shell extends it just a tiny bit. So we have a bigger anion. So it has a bigger anion than the normal atom. So we have 2 minutes left, so let's do just a recap of what we did. We did a lot of work today. So let's go back and look at what we did today, and I'll show you how much work we did today. When we did this much work, which is actually quite a bit an hour. So let me just review what we did for today in the last 2 minutes of our lesson here. So what we did was we talked about the isotopic abundance. So we reviewed what it was and how I showed you how we calculated, right? So we have atomic mass equals isotopic mass times the abundance, percentage abundance, plus isotopic mass times percent abundance, and so forth and so on. In this case, we had 2. In the second question, we had 3, right? So it depends on that. What we learned about was we actually had to make a equation, right? We said let X be, for example, in this one is let X be percentage abundance for silicon 28, let Y be percentage abundance for for silicon 30, and then we made an equation to help us solve in terms of one variable. We wanted to solve everything in terms of X, right? So solve everything in terms of X. So we got that, and then we just used algebra to solve for our percentage abundance, to collect like distributive property, collect like terms. That's review. So we got that. And then we talked about trends. We just did one trend today, which is simply just atomic radius and atomic ionic radius. But again, the point is, and you'll thank me in the next lesson when we talk about the other stuff, electron affinity and ionization energy, it all goes back to atomic radius. So if we get this concept down, the other concepts are much easier. So again, atomic radius is how big an atom is. As we go down a group, it increases. So remember my example of lithium and sodium here. I have 2 energy 2 shells. This is 2 shells, and I have 3 shells here. So it's much bigger, so we're good. Across the period, it decreases, right? We talked about this, the effective nuclear charge, and how if we have the same amount of electrons and protons, it likes to pull towards the nucleus, so it makes it smaller. And then our last thing was the ionic radius is the size of the ion. Again, cations are smaller than atoms. Again, cations here, I have 1 shell instead of 2 shells for my normal atom, and anions are larger than atoms because we have 2 shells here in this case, but F minus has an imbalance of protons and electrons, right? I have more electrons here, so it's going to pull further away. So for next time, we're going to go over these transition ionization energy, electron affinity, and then some reactivity stuff, and then that will be our next lesson. So as always, thank you for watching, and I hope you have a great day.